I'm going to start my third lecture, and where we left off with this statement, which was that after we have seen how to simulate, how to simulate this evolution of structure in the universe, and we saw what we have learned about it. I was making emphasis that these are actually predictions that are very important to understand about fundamental physics, about maybe the nature of dark matter and nature of gravity and departures from cosmological constants and so on. So if you keep that in mind, then it becomes very important that we don't stay with the same set of assumptions in a numerical simulation, but we drop, relax, vary our assumptions, right? We can cover different set of cosmological parameters, different type of dark matter, and so on. So I'm going to start this lecture by reviewing a bit of what these modifications mean and how we implement them and what they have taught us about structures. So far we have considered this very simple case, right, in which dark matter is the only component that we were simulating. We assumed that was cold and collisionless. We started with Gauss initial conditions, GR, and also we assumed that dark matter was a classical particle, meaning that we have neglected all quantum effects. We have seen that, or we have assumed that the dark matter interacts only classically through gravitational interactions. But all these things can be dropped and can be tested, right, with numerical simulations. In particular, we can drop the assumption of dark matter being cold, and we can simulate warm dark matter. We can simulate self-interactions of dark matter. So when you have two dark matter particles might suffer some scattering events. We know that dark matter is not the only ingredient in the universe, but there are baryons and other components like neutrinos. So the initial conditions might not be Gaussian. Actually, in fact, most theories of inflation predict that the initial conditions are actually not Gaussian. So we should test what the impact of that is in our structure formation simulations. Also, we can change the law of gravity and start simulating modified gravity. And also, we can drop the assumption of classical particles, and we can have what is called axion, wave, or fuzzy dark matter. Right? So each of these topics is its own field of research, and there is a lot of progress being done by many people around the world in each of these subtopics. So I wanted to start with the physics that we know we are missing, and in particular, variance. So imagine that soon after inflation, right, we have this quantum fluctuation that's been amplified, and at that point, dark matter and baryons have exactly the same spatial distribution, right? The same amplitude, the same phases. But this is not longer true as soon as the photons start interacting with baryons through quantum scattering. In particular, this scattering creates oscillations in the baryon photon fluid and stops the growth on small scales. So this is what is the origin of baryon acoustic oscillations and all the baryon, all the acoustic peaks in the CMB. So while the baryon is oscillating, the fluctuations keep growing, then radiation pressure counter-interacts and decreases them, and then gravity again dominates and push back the gas together again. Dark matter is not coupled through photons, so it keeps growing, right? There's only a tiny effect due to the residual coupling through baryons, the gravitational interaction through between dark matter and baryons. But most of it, for most of the part, the dark matter keeps growing. Essentially, it's only halted a bit by the Mesaros effect. But after recombination, the sound speed of this plasma drops by like 5 orders of magnitude. The Jeans mass drops by like 15 orders of magnitude, and then the baryons stop being coupled with photons, and the gravity essentially is the main force to dominate, right? But the important thing to realize is that at that point, and you can imagine redshift 1000, a few hundred, the distribution of baryons and dark matter is not identical. right? So they started from, so for instance, baryons have these huge oscillations that similar to what we see in the CMB, whereas dark matter has almost no oscillations. So this is what we see here is the ratio of the baryon power spectrum to the CDM power spectrum as a function of redshift and as a function of scale. So initially, the baryons have roughly half of the fluctuation amplitudes than CDM, right? So the CDM was much more clustered. And as time goes by, we go to lower redshifts. This difference starts becoming smaller and smaller. And then, in particular, the baryonic acoustic oscillations are imprinted from the baryons into the dark matter, right? And this is the feature that then many galaxy surveys have measured, and now it's used as a standard cosmological test. So we would like to test to add these effects in our simulations. So for that, we need to stop simulating only one fluid, and we have to simulate two fluids, each of which has their own fluctuation spectra and velocity spectra. So operationally, how we do that is, you remember the Seldovich approximation, that was essentially this. But now baryons and dark matter are not, no, the initial positions are not sourced by the same gravitational potential, but actually you have, each component has its own gravitational potential, and the velocities also are not the same, not generated by the same potential as the densities. So you actually need 4 potentials, and you create the initial conditions like this. And also you can, now you have 2 types of particles in your simulations, and you cannot put them on top of each other because they would very quickly become a tightly bound pair. So you tend to interlace them, like in this sketch, that baryons, for instance, could be the dark points and dark matter, the light ones, right? So you have to interlace them. Now you can now run your simulation and see these physical processes I was describing before. But before that, you have to be very careful with these simulations because now numerical errors are actually quite visible. So in particular here, I'm showing you how the ratio of the baryons to CDM and what you expect from linear theory, this solid line. And all the symbols are different embodied simulations with the same initial conditions. And the only thing that varies is how we compute the force field, in particular, the value of the softening length. So we see here that runs with very small softening length actually not reproduce at all the evolution that we expect from linear theory. And it's only when we assume softening lengths of the order of the mean interparticle separation, these 2 curves, is where we can reproduce linear theory, right? So again, this is another example of the discussion we had in the first lecture on how to choose the softening length. This case is telling you that choosing them to be according to the mean interparticle separation is the most faithful way of having a proper representation of the physics in the universe. Right, so now we can ask a couple of questions. How good was our approximation of assuming that the whole mass field was given by a single component? And this is, the answer is shown here, is the ratio of the total mass power spectrum between having simulated baryons and dark matter to having simulated only one single fluid, the dark matter. You see that the differences are very, very small, like below a fraction of a %. So if you are interested in only on the mass field, assuming a single component is actually a very good approximation. Yes? Right, so he's asking what is the origin of these discrepancies. So the origin is that now, essentially now you have the baryons have very little power on a small scales, right? So actually, you don't see it here. So have small power on a bit less power on a small scale, so the amount of nonlinearity that it produces is slightly less than if you had assumed, No, this is. Right, so these are runs without any hydrodynamic forces. There are still two fluids that interact only through gravity, and the only difference is that they started from different initial power spectra, right? So it's a more realistic description of what's happened on large scales. But then if you're interested, so that's true for the total mass field, but if you're interested in a particular subset of particles, for instance, the Lyman alpha forest is sensitive to the baryons, not to the total mass. then you might care about what is the distribution of baryons, not the distribution of the total mass. And actually, there's not that the difference with respect to the total mass now is not as negligible as before. So the same type of plots, and these different lines at different redshifts, and you can see that even at redshift 0, the baryons tend to cluster on very large scales, like about 1% less than the dark matter, right? So these are small effects, but they're of the same order of the accuracy of future surveys. So these effects might start being necessary to take into account. Now we also can see how the baryonic acoustic oscillation grows. Yes? Right, so these are essentially given by CAMB or class. So it's Boltzmann codes at a combination. Essentially, you evolve them until your starting redshift, and then you initialize your baryons and dark matter according to not the total mass power spectrum, but the baryons according to the expected baryon power spectrum at that redshift, and CDM according to the CDM power spectrum at that redshift. And then you evolve them forward in time. So now we can also see how the baryonic acoustic oscillation is different in dark matter and baryons. So this is what is shown here, the correlation function of distance. So you see from baryons, for instance, at high redshift, this was the initial one, the baryonic acoustic oscillation was very, very prominent. And as time goes by, the amplitude decreases. This is because the dark matter that was initially smooth is actually washing out this signal. And on the other hand, the dark matter that actually had a very small BAO at the initial redshift, it starts having a more and more prominent signature. Right, but so as I was mentioning, this was a purely collisionless case, neglecting whole hydrodynamic forces. But we know that there's not the right assumption to make on very small scales. And in this plot, I'm showing you what to expect, right? So and how we can build models for it. So this is the density profile of a typical halo, and it has a very busy plot. You have many lines. But I'll try to explain them. So the first, in the dark matter only, you will have a profile that's described, for instance, by an NFW, as I was showing you earlier. But when you have baryons, hydrodynamic forces, star formations, and so on, you have other components. For instance, and the very center part, you will have a galaxy. You can assume that, for instance, has some sort of an exponential profile, and this is going to be above this bluish line, which is the dark matter only case. Right? So in the central part of the halos, the density is higher because of the galaxy. Then you know that a fraction of the mass will be in form of a gas in more or less hydrostatic equilibrium, and this is the profile you expect for that. So this is the red line. You can assume that follows more or less this profile, right? And then you have a third effect, which is because of feedback effects. A fraction of the gas is expected to be expelled from the halo, right? So you have a black hole or supernovae that are pushing gas away, or also stopping gas from accreting, because you have this outflow, so it stops gas. And so you have a third component, which can be, you can call them an ejected gas, which would have a characteristic scale given by an ejection radius. Right? In this case, is here, right? So when you put these ingredients, and then you have a fourth ingredient, which is if you have all these different components that distribute differently than in the dark matter only case, the dark matter in the full physics case would actually be modified because of now the potential weight in the center is deeper due to the fact that there is a galaxy there. So that is another effect that you take into account. So here's a summary of all these effects and their impact for the total mass power spectrum. So this is, for instance, the central galaxy. So what it does is increases the amount of nonlinear power spectrum on the very central parts. And then you have the ejected gas, essentially that suppresses power on scales essentially smaller than this typical ejection radius. And these effects could be of the order of 10%. Right? So for comparison, this is a compilation of the same quantity, but measured in a set of state-of-the-art hydrodynamic simulations. So in particular here, this one, you see first that all of them have qualitatively the same shape that we were expecting by this description I mentioned before, but the strength is different, right? So the illustris, this very famous hydrodynamic simulation, is this line, actually predicts very strong effects and up to very large radii. Other simulations, for instance, the Eagle is this guy here. It's much smaller and confined to smaller radius. And in fact, now the predictions of Eagle are very similar to the newer version of Illustris, the Illustris TNG, and all of them seem to agree that these effects are essentially important above K of the order of 3 or so. This is another simulation, Owls, that has also very strong feedback. And now we look at these plots and we can understand what is going on. We see that this scale and the suppression is primarily given by these outflows and the ejected material. Then the average suppression of this is given by the amount of mass that was expelled. And on small scales, you have an increase again due to the presence of the galaxy and the consequent adiabatic contraction that it exerts over the dark matter. Right. Anyway, so the question is why the curves deviate from the dark matter only case different scales, right? So the scale at which you deviate is roughly given by the maximum scale up to which you eject gas, right? So if essentially you eject gas up to 10 megaparsecs, the scales of the suppression would be roughly pi over 10, right? So, right. So then you ask, what sets this scale, right? And essentially that scale is set by a balance between gravitational forces that want to keep the gas here and the energy that this outgoing material has. So different simulations assume different recipes and inject energy in different ways. And some of them you could imagine that even if you inject the same amount of energy, you still have to decide whether you inject it in terms of momentum or thermal energy, for instance, right? So if you put all of it in momentum, you're probably going to expel something very far. If you put everything in thermal energy, you don't move them. You make just the gas hotter, right? So the different choices of different simulations result into different effects on this power spectrum, which is actually quite nice because you can imagine in the future we would be able to measure that, and then we could constrain the effect of outflows and baryonic physics too. Yes? The ratio of the ejected and bound gas, again, that depends on the physics that you implement and the same considerations as before. But typically it's only a few percent of the could be 5% or something like that. So whether that depends on the halo? Whether it depends on the relaxation state of the halo? No, I don't think that it depends, at least not at first order, because essentially the amount of energy that is given by, the simple models by two things, essentially the mass of the black hole and the accretion rate, right? So that it's a very local process. And then you have to choose essentially how you are going to inject this energy, right? And then it could be energy, momentum-driven feedback or energy-driven. And most people tend to choose momentum-driven because the energy one is actually does not suppress much star formation. The gas tends to cool down very quickly after you put some energy, and then you keep forming stars. Yeah. So another ingredient that we know should exist are massive neutrinos. So there are, in the standard model, neutrinos are massless, but there are several experiments that indicate that neutrinos have mass. And in particular, if they have mass over the order of the lower limit that we know from these experiments, they should affect the structure of the structure in the universe. So it's an important thing to consider, right? So in particular, these neutrinos at the very early time, they behave as radiation. But as the universe expands, these neutrinos cool down, they eventually become non-relativistic, and then they can cluster and affect the structure formation. So one particular or peculiar property of neutrinos is that they are very hot. What does it mean? Is that they are very light, so they move very quickly and on all directions. So in these phase space plots that I've shown you already, right? So we had the case for cold dark matter that essentially was like a straight line. For a given point of position, there is only one velocity that's available. For the case of warm dark matter, you can imagine that this line or this manifold has some finite extent, still very small, but for neutrinos this is very, very large. It means that at every point of space you can have many, many different velocities. In fact, they're actually distributed as a Fermi-Dirac distribution. So you need to simulate it in a very different way than you did for cold dark matter. So there are different implementations that people have adopted. I'm just going to mention the two extreme. The first one is that you can solve the neutrinos with a Boltzmann code, a linear perturbation theory, and in your Poisson equation, remember that this was the density. So now it's not only the density of your mass in your simulation, but you can add the density due to neutrinos, and then you can, that is going to be, it's going to back react onto the mass distribution because it's part now of the gravitational potential, and then you keep evolving. This is actually not a bad approximation, but misses a lot of the nonlinearities and the back reaction of the nonlinear mass field onto the neutrino distribution. And the other extreme is to Monte Carlo sample the full distribution function in the same way that we were doing it on space, right? Now we are doing it also on the velocity extent, right? So for a given position, now we can sample all different velocities with a few particles, right? So what we have learned from this is that neutrinos suppress the growth on small scales. So here's an animation switching between a case with and without massive neutrinos. And I'm not sure you can see well, but the effect is that the growth of a structure is halted by neutrinos, right? It's like, this is like, you can imagine it's like it's a fraction of the mass, and now is in form of neutrinos that moves very quickly, very far away. It's hard to cluster. So it's like you had less mass to start with. So this is a more qualitative plot that shows the suppression of in the power spectrum induced by neutrinos. You can see that depending on the mass of the neutrinos, the suppression is different. It's actually is proportional to the fraction of the mass in neutrinos. So because the total mass field is different, now it's also the Hello mass function is affected. Now this is the ratio with respect to the Lambda CDM mass function. You can see that, so again, for different neutrino masses, that the abundance of massive clusters is reduced with respect to CDM. I think I'm going to skip that one. Right, so these were ingredients that we know should exist, baryons and neutrinos. But no, despite decades of effort, we still don't know much about dark matter. No, we don't know its properties, its mass. So we should keep our mind open and explore different possibilities for dark matter. So I'm going to review quickly 4 different ones. One is warm dark matter, or the case in which it's made out of neutralinos, and if there is self-interaction, and also axion dark matter. So the warm dark matter is an interesting case. So before we were assuming that dark matter was absolutely cold, but now if it's warm and if it's, again, means that it has a small but finite velocity dispersion on small scales, right? So it cannot be considered really that has only bulk motions, has some thermal random motion. So now you can imagine the early universe, if you had a fluctuation and now you are a dark matter particle sitting in the middle, if your velocity is large enough, you can actually escape from this peak of the density, right? So more technically, there is a free streaming scale, and all fluctuations below that free streaming scale get washed out. So this is what is shown here, the same power spectrum as a function of k, and the different lines show the type of suppression that you would expect with respect to the cold, this is the dashed line, for different dark matter masses. So if you have something very light, like 0.25 keV, you have a suppression of the order of unity. In this case, you don't form clusters and barely form Milky Way type halos. If you have now between 1 and 5 keV, now the suppression happens in the same way, but now on smaller scales. And actually, this would suppress the formation of like small dwarf galaxies. Actually, the constraints on the best constraints on warm dark matter are about 3 keV, so it would be about here. Or there has to be, no, this is the upper limit, right? And then if you have a 10 keV particle, then the suppression happens on even small scales, and probably at this point becomes indistinguishable with at least galaxy formation, right? So galaxies, we see that galaxies are not affected essentially by these very small structures. Right? So in the same way that neutrinos was making the distribution function to be very hot, now the warm dark matter case something intermediate, but the velocity is much, much smaller, right? For these cases, even this very massive one, the typical velocity that you expect at redshift 0 of the order of kilometers per second, fractions of a kilometer per second. So if it doesn't really, it's actually very, very small. So typically, actually, almost all simulations of warm dark matter, what they assume is that, the warm dark matter is actually cold, but the initial fluctuation spectrum is given by one of these truncated ones. So you kind of erase the initial fluctuation and then let it evolve as a cold fluid. Yes? Right. So if I understand the question correctly, you're saying, so it's very clear the suppression that on a small scale, but does it have any effect on the BAO feature? And right. So the easy answer is no, right? So the BAO is a very, very large scale feature, right, of the order of 100 megaparsecs. So in principle, if you have something very, very warm, then they would be erased. But for that, you need to erase essentially all the structure up to 100 megaparsecs, so you would not have any dark matter halo whatsoever. Right? So the current constraints that come from galaxy abundance are about essentially suppressions around here. You see that BO is very, very far away. So it's mostly, BO essentially is a geometric probe. So it just cares about the amount of mass in different ingredients, not so much about the growth. What it does, might be sensitive, actually, could be redshift space distortions on these small scales. But even that, I think, is on the borderline. Yes? So how this correlates with the missing satellite problem? Right, yeah, it's an interesting question, because actually, there was a revival of these ideas of warm dark matter because of the missing satellite problem. As I was, actually, I'm going to show this in 2 slides, so let me come back in 2 slides. So I wanted to show you a movie of how structure formation happens in warm dark matter. If you recall in our previous movies, there were a lot of this granularity initially that can start merging and bigger things happen. Warm dark matter is actually different to that. First, you have very well-defined filaments, and then these filaments collapse very quickly, and a huge halo forms immediately. Right? There are some halos that actually don't have any progenitors. They quickly appear, and then they keep growing. In that sense, it's really a bottom-up formation. There's no bottom-up formation. There is a kind of a monolithic collapse of large structures. And then there are also other consequences, in particular for the internal structure and for the abundance of substructure that is related to the missing satellite problem. So this is a simulation by Mark Lovell, where he simulated a halo with cold dark matter and with warm dark matter. And you can see that the overall distribution is kind of the same, but in CDM you have all this small scale structure, right? So this is the remnants of this small scale, of small mass halos that were being accreted, right? Because there were no progenitors in warm dark matter, there are no such structures. So you have very few satellites, right? And actually the amount of satellites depends on the mass of the dark matter. So you could, in principle, use this because you could say, you can go and count satellite galaxies and see how many of them you have and compare them with how many you have in warm dark matter. And yeah, so that based on that counting, you can also put constraints on the amount of dark matter. There are also some other effects on the internal structure of of these dark matter halos. In particular, they become less concentrated than CDM halos. If you remember in the previous lecture, the concentration-mass relation formally is different than in CDM. So now halos are less concentrated, and that might help towards this core cusp problem. Right, so what about if we consider a realistic cold dark matter? Right, so several supersymmetric theories could tell you that you might have dark matter made out of neutralino. This is one of the lightest supersymmetric stable particles, and even though it's formally a cold dark matter, it still has similar effects as the warm dark matter, but on very, very small scales. For instance, for 100 GeV neutralino, you expect the suppression to happen not at galactic scales or dwarfs or anything, but actually on mass scales close to the Earth, so 10 to the minus 6 solar masses. Right, so this is the full. They would provide a full hierarchy of structures in a consistent cold dark matter. Right, that you need to have structures all the way from 10 to the minus 6 solar masses to 10 to the 14. Unfortunately, for that, to simulate that, you would require something like 10 to the 20 or so particles. It's very hard. So when we need to understand about this structure formation, this scenario, we resort to other type of simulations. It's not where we focus on a very, very tiny region of space and at high redshift. I'm going to show you a movie of this. I'm not sure you can see well, but this is a region of 1 kiloparsec. Just keep in mind that before I was showing you always regions of order of gigaparsecs. So you can see it again. So that is one difference. And now in the whole region, there are 50 solar masses. You can also get an idea of how actually the universe is not very dense, right? So it's 50 solar masses on a region comparable to the size of the Milky Way. So now you see that also something similar happened to the warm dark matter, that you don't have structures below some scale, and then the structures collapse and become massive very quickly. In this case, you see 3 huge regions. So we are going to zoom into the formation of the first halo that you expect on this neutralino CDM, it's an Earth mass halo. So each of these, you see filaments like in warm dark matter, and then you see all these clumps, which are Earth mass. And there is a period in which they have very violent history, that you have multiple major mergers going on, and then larger halos form. And we stop this movie at when the halo gets to about a solar mass. Yes? I'm going to come back to that. So he was asking about this pattern of looks like interference pattern. Right. So when we look at them, now we can see how the density profile of these first halos are. So this is what is shown here. The density is a function of distance to the center as a function of time. So the red is early time and blue is late time. These are only at about redshift 30, right? So nobody still has managed to simulate one of these scenarios all the way down to redshift 0. So you always have to stop it at very high redshift. Then you see that there are different periods or stages of formation. First, you have these filaments that collapse, and then they form these single power laws that have a very sharp transition, very sharp cutoff. It's very different to NFW halos, for instance. And then there's a period of mergers, and in that period of mergers, violent relaxation is at place, and the whole profile relaxes to something quite different, more looking like a broken power law, something similar to NFW. And then once this profile is established, the halo keeps growing and nothing much happens afterwards, right? So this may offer some ideas about how the density profile or the universality of the density profiles form. Okay, so this was this neutralino dark matter. We can also have self-interaction. So we can have 2 dark matter particles on small scales, having a non-zero cross-section, and there will be elastic scatterings. So you remember the Vlasov-Poisson equation that I was writing earlier? Before, we were always assuming that the right-hand side was 0. There are no collisions. In this case, there are collision terms. And this is an expression for the expected mass to be expelled out due to collisions. So there are terms that depend on the relative velocity between two fluid elements, the cross-section for interaction, the density of them, and the distribution function at that point, integrated over all possible velocities, right? So how you do in practice? You try to estimate this probability. Now you have a set of particles, and then you want to estimate what's the probability that this particle is, or that a pair of particles suffer a scattering event. And this probability is proportional to the amount of density, right? So how many, the more dark matter particles you have, the higher the chance of scattering. The relative velocity between them, and the cross-section, and also your time step, right? So you want to compute this probability per step, and then you draw a number between 0 and 1, and then you can see whether a particle is, a pair of particles gets scattered or not. And then you go and do that over one step, and you go do that next step, and so on. So when you do this type of simulation, you find several effects. The first one is actually that halos become rounder. Now you can imagine that if there are two, if the scattering is significant, the angle in which the particle is going to be scattered is isotropic, so you tend to erase all the initial anisotropy. Actually, this is a plot showing the projected mass distribution for a halo with a very high cross-section compared to the CDM one. Actually, you can see that the ellipticity is very different. And actually, some of the best constraints on the dark matter cross-section comes from measuring the ellipticity of galaxy clusters through gravitational lensing. The other thing that you see is that the amount of substructures is different. So now, because of I'm going to go there in a second, but the density profiles are also flatter in the center. Well, we can just go here, right? So this is how the density profile changes for different cross-sections with respect to CDM. So now you can see that the larger the interaction cross-section, essentially more scattering events you will have. So then the density in the center, which is where you have most of the mass, therefore most of the scattering happens, is going to decrease. Actually, as you increase the cross-section, the density goes down, down, down. Actually, there is a point in which it goes so much down, and then actually you don't keep going down, but actually the whole center goes undergoes like a core collapse event, and the density actually increases a bit. But that's second order effect. Right, so now because of the density profiles are flat and the center are chord, the subhalos, which are again the descendants of high redshift halos, will also have cores, and when they are in the strong tidal field of the host halo, they would be more easily disrupted. That's why you end up with less structure when you have a self-interaction than when you don't. And actually, also this was another motivation to solve for the too big to fail problem and the missing satellite problems. Sorry? Sorry, I cannot hear. The interaction? Whether it will heat up? Actually, yes. So the velocity dispersion actually goes up also in the center. Yep. Okay, so and then I think it's going to be the last modification I wanted to discuss is axion dark matter. So far we have assumed that dark matter was a classical particle, but there has been the suggestion, Rashid also mentioned it yesterday, that dark matter could be made of axions. Axions are particles that are well known in particle physics, that could be non-thermally produced at very high, essentially a very high redshift. And one of the peculiarities is that they would be described by a single wave function. And then there is essentially the uncertainty principle would create like a pressure term on small scales, and it would also suppress small scale structure in the same way that warm dark matter, right? And the dynamics of this, and now you have to not solve the Vlasov-Poisson equation as in our case, but in this case it's the Schrödinger-Poisson equation, which has this form. And the waveform, the amplitude squared, this could be the density. Right? So now you can go and simulate this, this system, where typically with AMR codes, and and then and see whether they could reproduce or not what we know about the universe. So this was a paper by Shiva et al. In 2014, where you show the distribution of clusters and filaments in cold dark matter, and then it simulates the same Gaussian random field, but with this wave dark matter. Right? You can see that the large-scale structure is pretty much the same. It's actually on a scale larger than the typical wavelength of this quantum pressure. Essentially distribution of mass is going to be identical. But on a small scale, they're very, very different. Right? This is a zoom in on one of those halos. And now you see several effects. So the first one is the density is not constant, but actually has all these granularities. And actually this evolves very quickly in time. It's not stable, but it has a very high frequency. And the other nice or surprising effects is that if you focus on the very central part, this is a zoom in, and this case we zoom in, it's actually a core. This is like a soliton solution. It's like a standing wave that would be in the center of all these halos. So here's a plot showing you the same. This is the density profile as a function of distance from the center for halos of different masses. This is the NFW, right? So r to the -3 outer parts, r to the -1 in the central. And when you simulate the same structure with this wave dark matter, in the outer parts are pretty much the same. But the central part, there is of this core that's a very distinctive feature of wave dark matter, and it's actually the motivation for several ongoing searches that they try to estimate this density profile to high accuracy or other ways in which one could detect this soliton on the Milky Way, for instance. But unfortunately, when doing this type of simulations is very, very expensive. So you need to have extremely high spatial resolution, and also a very, very high time resolution to resolve all these oscillatory patterns. So typically you can simulate only kind of 2 megaparsec boxes or so, no more than that. So when you want to make predictions for the overall distribution of galaxies abundance and so on, actually, even the same authors resort again to the called collisionless approximation. But now the initial power spectrum is given by what you would expect in this model, not the CDM power spectrum. And that actually is a very good approximation. And now you can quantify, for instance, how many halos of different mass you have at different redshifts as a function of the boson mass. Right. So now I would like to, the last 10 minutes. Before, are there any questions so far? No. So so I wanted to go back to the interference pattern that you probably saw in many of these cases. So in warm dark matter, we saw that the filaments were actually not smooth, but actually were breaking into pieces. Right? The same thing with in the simulations of the neutralinos, that you see this filament that actually should be something smooth, but breaks into pieces. Right? And the same happens in even axions that actually fragments here. So these are not, initially people thought that maybe it's a numerical, it's actually a physical effect, but now it's a consensus that it's a purely numerical effect. Right? So it's actually now is known as artificial fragmentation in numerical simulations. So I wanted to explain the origin of this. So as you might recall, we had our distribution function that we Monte Carlo sampled, and then we had the equations of motion. We were computing tree and or particle mesh and so on. But something important to realize that out there are many codes. I mentioned Ramses, PIKD graph, Gadget, and so on. But all of them rely on the same set of assumptions, the same as coarse graining of the initial distribution function. They only differ in the way that they compute forces. Right? Everything else is essentially the same. Right? So then all of them actually suffer from the same artificial fragmentation. Right? So the origin of it has to do with the softening length. Right? So we were talking about these two competing requirements in setting the softening length. On one hand, you want a relatively large value of the order of the mean interparticle separation to reduce discreteness effects, but also you want something small that so you resolve the small scale structure. right? So then this actually, when you end up using values typically in all modern simulations of about 1 to 2% of the mean interparticle separation. But actually this leads to the following problem. So imagine that you have a homogeneous distribution of particles, like on a regular grid, and then you have an anisotropic triaxial collapse. So essentially you collapse along one direction. So what was initially uniformly distributed, now imagine that you compress it in this direction. Now you end up with this configuration, and actually instead of describing a uniform line, actually what forms is 4 different clumps. And remember that this is a dynamical system. So the forces will respond to this new distribution, and actually these objects might collapse with attract even more mass, grow, and even be realized, right? But these are just, you can imagine that if you had more particles, now this fragmentation would occur somewhere else, right? So now it's very clear to see that this actually has a numerical origin, right? And it's something intrinsic to our choice of discretization of the phase space fluid. So how can we solve for these problems, or at least test whether these are important or not? Now, keep in mind that these numerical simulations would be very important and fundamental for constraining this dark energy, dark matter, and so on. So we need to understand all these effects. Right, so an alternative way of doing the discretization can be thought as the following, right? So we have the distribution function, and now we had a set of points. But you might not have wanted to choose points. You can actually perform a full tessellation of this phase space sheet. You can imagine that instead of sampling here points, we actually discretize it as a set of disjoint but space-filling volume elements, right? And now we can actually try to follow the evolution of these phase space elements, right? So this is showing you how it would look like now. These points in the space are the vertex of this tetrahedra in this case, and then they start determining what is the evolution of the flow, right? So they are in the standard embodied case, the mass is actually at these locations, but in this new approach, these are just mesh generating points, and the mass is in between neighbors in Lagrangian space. And then you can track them on as time evolves, and actually these elements can be superimposed, can stretch, and move, and towards essentially move, tracking the distortion of the fluid. So you can even actually take this idea and say, well, because now we know where the mass is because of this tessellation, we can put them as a source for the Poisson equation and actually do simulations that are self-consistently evolving through this tessellation of phase space. This is something we did in a paper back in 2013. And now you can see that, well, I'm not sure you can see well, but before in a standard runs, you see all this fragmentation. And when we do this, now we don't have this problem of this that I was mentioning with the triaxial collapse. And now filaments are truly smooth cases, true structures that don't suffer from any artificial fragmentation. It's another example. Let's zoom in on the formation of the collapse of a filament. And yeah, I'm not sure if you can see well, but it's essentially the same. Right, so this idea actually worked out to be quite nice to get rid of this artificial fragmentation, but has a problem. That is actually because we are tracking the deformation of this dark matter sheet with all the nonlinearities, the fluid becomes very complex very quickly. Right? So let's go back to these phase space plots. Now imagine that you have a set of points describing this is a Celovich pancake. And now you can see what the this Lagrangian tessellation is in this 1+1, which essentially is just connecting two neighboring particles by a straight line. And assuming that the mass is not on these points, but actually is on the connecting lines. I mean, seems to be a very good approximation to what you would imagine the underlying true distribution function is, right? As time goes by, you start seeing all this wrapping of phase space. We saw it in the first lecture. And now you start seeing some places where it actually kind of fails, right? So now it should have been like this, but we are approximating as a straight line. When it's even more complex, the problem is even more severe. And actually, it's a nasty property because the error that you're making is not random, but tends to always go putting mass more towards the center than outside the halo, right? So halos would actually become more concentrated, and the properties of them would be biased. So this was a problem that we wanted to tackle in a paper in 2016. So instead of taking only tetraedras, we generalized the method to a full class of phase space that you can imagine now you have volume elements that are maps between Lagrangian and Eulerian coordinates. So we dropped this idea that we have particles and mass, and now we have just maps between these two spaces, and the only thing we need to do is to describe these maps accurately, right? So you can imagine that the map can be described by a polynomial of an arbitrary degree. Okay, so I think we'll skip some stuff. So one of the nice things that you can do is actually that these maps you can detect the places where this approximation fails, and you could add some adaptive refinement of these maps, so they can keep tracking correctly the deformation of the dark matter sheet. So, but now we have a method that is actually unbiased, but becomes computationally expensive, too expensive very quickly. So, so one way of solving this is actually to have hybrid methods that combine the best of both worlds, right? So in low density regions, and early times, the sheet approximation is very good, but then we want to switch to a standard n-body once particles are inside the halo and the wrapping becomes too complex to follow numerically. I think I'm just gonna. Right, yeah. So this leads to the geodesic deviation equation. It's a very interesting equation that asks, let's consider a finite volume in phase space, and let's ask what the evolution of this phase space volume is. Right? So you can imagine that you have delta x and a delta v, and we want to represent this as a function of time of the initial essentially volume element, right? So you can actually write equations of motion for how this volume element would evolve with time, and that is called the geodesic deviation equation. So it's telling you how the space on a given point is being deformed, how the phase space is being deformed, right? So in position and in velocity. And you can go and estimate with this what is the density that you expect, and compare that with the density that we estimate using the tessellation method. So this is a comparison in Lagrangian coordinates. So all these large clumps is all the mass that's going to end up in a single halo, right? So if we would have done this in Eulerian coordinates, this would be a small halo, a filament, another small halo. And now you can see that on low density regions, the sheet method agrees very well with the geodesic deviation equation, but in the center of halos, they fail. So we are using this information to switch. And okay, I think I'm going to skip that. Right. So, and I think that would be a promising way of improving numerical simulations and get rid of many of these numerical effects and more faithfully represent phase space. So I wanted to finish my lectures with a couple of slides mentioning what are the open problems and challenges in the field. So the first one is that observations are way ahead of theory of numerical experimentation. So it's how can we catch up? I was telling you in a few places during my lectures that we still are not able to simulate something as accurate as big as the Euclid mission. Actually, that's even true for the Sloan survey. It's a very famous survey, and still there are no simulations that could resolve at the same time the large volume that is observed, and the smallest halos that host the galaxies visible by Sloan. Right? So this is actually a problem. So we need to start pushing our boundaries to be able to make predictions as accurate as observations. So another question is how can we increase the accuracy and precision of embodied simulations in the light of them being used for fundamental physics? And I mentioned a possible method to do that. And also I guess I mentioned that you need to be very careful with numerical results. And also that we have a reasonable theory for how structures form. I show you how successful we are in reproducing the distribution of galaxies and their internal properties. So now I think that one of the next questions for this field is how we can use everything we have learned to directly start interpreting data, maybe with these forward modelings that Ben was telling you, or some other ideas that we can start using, that the fact that we can reproduce the universe very well. So how can we actually start taking that and using it directly to do, for instance, cosmological parameter estimations and so on. So another question that remains open is that we are still not able to resolve the full hierarchy of structures in cold dark matter. So maybe after 2050, if the supercomputers, we could be able to resolve something like that. We need to be focusing on, for instance, the kinematic of stars on the smallest dwarf galaxies, because those are the places where the nature of dark matter would show up more clearly, where we can start distinguishing warm dark matter from self-interacting dark matter from cold dark matter. So we need to start simulating whole Milky Way halos with enough resolution to do this. We still don't know really what the origin of these NFW profiles are. I think there have been several attempts, but it still is an open question why halos have the density profiles that they do. We need to understand and make predictions for the phase-space structure that also could be relevant for direct detection experiments, and understand the role of the Milky Way, the changes in the potential, how that is affecting the structure. And we need to also improve our microphysical description of the physics. I mentioned to you in neutrinos, for instance, that we are doing currently very crude approximations. And the same is true for self-interacting dark matter, where we approximate everything as these big cold macrophysical particles. We don't know whether those are correct assumptions or not. So hydrodynamics and galaxy formation is another important topic that needs to be addressed. So we're still not clear what the degeneracies are between cosmologies and what the impact of between cosmology and galaxy formation, whether the effect of neutrinos can also be mimicked by a particular feedback model, right? So if you don't understand these things, we will never be able to say, hey, we detected massive neutrinos, right? So we need to understand this better. So I mentioned to you that Variance can modify the shape of the density profiles and the shape of the power spectrum on small scales. And even though qualitatively we understand them, we still don't know whether this is the right modification, right? So maybe the type of feedback that we are implementing in our simulations is completely wrong. And also, if we don't understand that, then when we try to measure, for instance, the impact of a particular ingredient, maybe what we will be constraining is or what will be limited is by our poor understanding of how galaxies form. And yeah, in that sense, we need to understand better whether the current implementations in hydrodynamic simulations are realistic or not, and in particular, improve the treatments of radiation and thermal pressure support and turbulence. And there's a lot of physics that goes into there. And finally, so I mentioned to you that the supercomputers are changing. So now we're going to have of the order of 10 million CPUs with very little memory per node, and we have all these GPUs, Xeon Phi. So I think a question will be how we take advantage efficiently of all those resources in terms of parallelization strategy. I mentioned some redundancy that in the previous lecture. We need to develop mixed algorithms. So, and I think it's also going to be very important because if we are able to do this, we are going to be able to do better simulations, new science, and also the motivation I gave you earlier that we can solve problems that we couldn't solve otherwise. Also, another aspect is that with the huge data sets, we need to start thinking in advance the problems we want to solve, and many of the analysis had to be done together with the simulation. We cannot, in many cases, analyze them in post-processing because we cannot maybe even store the data that is being generated. And then, related to that is that now we will have these huge data sets, so it's not obvious how you actually can distribute them globally and how to even analyze them. So this was a couple of points that I wanted to raise, and I hope you become interested in this, and I hope at least you solve some of these problems in the future. So this is my final slide with a cool simulation of the formation of a halo, and I wanted to also mention a lot of people who have contributed in one way or another to the results and plots and slides I've been showing you during these lectures. So that's it. Thanks for your time, attention. And I guess we have time for questions, or we break, or okay. Right. So the question is whether the method I described was the same as moving mesh. So not quite, right? So the moving mesh at EPO, they do a similar tessellation of space, but they always do it in Euclidean coordinates, right? So as you evolve with time, essentially you can rebuild the tessellation and so on. Whereas in this case, we tessellate only at the initial conditions, and the tessellation is fixed, and the tessellation then kind of have these elements overlapping and so on. More questions? Yes. Right. So the question is whether the warm dark matter simulations that use modify initial power spectrum, but with cold dark matter, also produce cores. So the first answer is no, right? So essentially warm dark matter, you expect them to have cores on very small scales due to space constraints. But the size of those cores are very, very tiny, right? So the main effect is actually changes in the concentration of these halos. Right? So on the scales that it would be important for galaxy formation, it's not the phase space constraint, but the changes in the overall profile, and that can be captured by these simplified methods. Okay, so I just wanted to mention one thing that, so at 5, I believe, there's a hands-on session. We have 1 hour. So what I wanted to do was to write our own little 1+1 dimensional embody code. So where we can do one of these phase space plots. And for that, you need essentially only Python. And the standard library is matplotlib or something. So I believe most of you, if not all of you, have laptops, and if you don't have Python, I think you can log into this to a server, right, where you can get a Jupyter notebook, I believe. So I think in case you want to be ready, just make sure that you know how to access the Python notebook, and that or that you have Python installed in your laptop, and the standard library is matplotlib, numpy, and these type of things. Okay.